So now that you've had a chance to learn about collect, let's focus on another very common terminal operation in the Java Streams framework, which is called reduce. So collect and reduce are by far the most common terminal operations we use in streams. Once again, we're going to use our Hamlet program to illustrate how this works. You can get the code here in EX12, and I strongly recommend going and taking a look at this code and try to run it. You can use it in IntelliJ, which is the underlying IDE that's used as the basis for Android Studio in order to do the actual computations and run the test programs. So the reduce terminal operation typically returns a primitive value. It doesn't have to, but by far that's the most common way to do things. And so we're going to look at an example that kind of riffs off of the Hamlet program to illustrate how the reduce terminal operation works. So again, just as we had just talked about in the collect discussion, let's assume that we've created ourselves a map that maps the names of characters in Hamlet to the lengths of their names. And we did that by having a stream and collecting up into the tree map, or the map as it matters here. And then we're going to take that map and we're going to go ahead and do some stuff to it to get the sum of the lengths of the character names. So we want to figure out, if we take all the characters in Hamlet and we add up all their names, how big is that? Why you would do that, I'm not sure, but it's a good way to illustrate the mechanisms that we have here for reduce, and to compare and contrast with other things like collect, and we'll do that later. So the first thing we do is we take our matching characters map that we got from collecting the processing in the stream, and we then say dot values. Dot values is a factory method that just creates a set of values, namely the lengths of the names, and then we convert that set of values, which in this case are longs, into a stream of longs. So we've got a stream of longs, and the next thing we're going to do is we're going to reduce that stream of longs. So what does it mean to reduce something? We'll take a more detailed look at what reduce does and how it works under the hood shortly, but for the purpose of this lesson, what we're going to do is we're going to sum up the names of all the characters in Hamlet using the sum method via a sum method reference, long : : sum. The first parameter that's passed to reduce is the identity value. It's the initial value of the reduction, which is 0, and it's also the default result if there are in fact no elements in the stream. So if the stream actually has 0 elements, which would be weird, but if it did, then the resulting value would be 0, which is exactly right. The sum of the name lengths of an empty stream is 0. It's also the identity value. Identity just means that that value plus any other value returns the other value you just added to it. So that's what's called the identity value. This method reference that's passed in, the long : : sum, is referred to as an accumulator. And an accumulator is intended to be a stateless function, meaning it doesn't have any side effects. And in this case, that stateless function simply takes 2 values and 2 immutable values, and then creates a single immutable reduced value by summing them together. And we'll talk in a bit more detail shortly. I'll kind of visualize for you how that all works under the hood. But just imagine that we're doing pairwise addition of all the different parts in the stream. You could also use a lambda expression here instead of using a method reference. So instead of saying this, you could say open paren x comma y, close paren arrow x plus y. Same exact thing, probably will run in roughly the same amount of time. I personally happen to like this better because I think it's more concise, but you can always write this and your code would not be incorrect. There's also a 3-parameter version of reduce that's the so-called map reduce version. And this is intended for use with parallel streams. Now, using parallel streams is overkill for something as simple as this example, but imagine we had a much larger example where we had thousands of character name lengths that we wanted to add up and sum. In that case, it might make sense to run these things in parallel. And if that was your choice, what we would do here is we'd say convert this into a parallel stream and then take all the elements in parallel and reduce them in parallel. So the way this is going to work is we're going to start out with an initial value of 0 as we had before, and then in each of the threads in the fork join pool, we're going to go ahead and perform the map operation. And the map operation is going to be computing a running sum in that particular thread of the lengths of the character names that are in that chunk that's being processed by that thread in the thread pool. And I'll talk later about how the thread pools work in the context of the common fork join pool and so on and so forth. After you've done all the computations in parallel, each one done sequentially, of course, but the combination of everything is done in parallel, we then have to do the reduce phase. And that's where we take pairwise results that come out of two threads. And in one of those threads, we sum the results together to create a new result. And this whole thing takes place basically in a tree of parallel processing operations. And when all is said and done, you end up with a single reduced result, which corresponds to the reduction of everything. And I'll show you again how that works in a visualized way shortly. But just in terms of what it's doing, we're going ahead and doing all the additions in parallel for the different threads, and then we're summing up the intermediate results of those additions and doing it successively as basically a binary tree. Think of an upside down binary tree. And by the time we finish the final reduction, we have a single reduced result. There's other ways to do this that don't require the use of reduce explicitly, although reduce is used under the hood in this case. You can use another method called sum. And sum is also a terminal operation. And as you can see here in this approach, we once again take our map of character length bindings, associations, turn the values, the lengths, into a stream. We then convert that stream into a stream of long primitives, because it started out a stream of long objects that are a reference type. And then we convert those into a stream of primitive operations by using the map to long intermediate operation. And then we take that stream of long primitives and we sum it up into a single reduced result. So that's how you could use sum. As to whether that's better than using reduce, it's kind of 6 of one, half dozen of another. It's maybe a bit more clear what you're doing, or maybe not. Either way works fine. And honestly, I think the runtime performance is roughly the same. You could also use collect to do this, ironically enough. You don't have to use reduce. So yet another way to do this is to use collect, and to collect by passing in you have a factor method, the summing long method. And what that does is we trigger the stream processing with collect, and then we use the summing long collector, which is created by the summing long factor method on the collectors utility class, in order to be able to sum up all the values in the stream after first converting them into long primitives. So this is yet another way of doing things. I'd have to sit down and do some benchmarking to see which approach is faster. They're probably about the same when all is said and done. But you can either use collect or you can use reduce in order to be able to create a single reduced result at the end of the computation. You can also use reduce to return non-primitive values. That's a little bit more unusual, but it's possible, although not always desirable, as we'll see here in a second. So here's an example that illustrates how this works. There's a program called EX17, which is in my GitHub repository, that has stream reduce concat. And what it does is it's going to have the reduce operation create a string, a single string that contains all the concatenated words in a stream. And the way it works is the first thing you do is you make the identity operation, which will be a string, which is immutable. And then the accumulator is simply going to concatenate the two strings, concatenate the next two strings together, and it'll keep doing this and doing this and doing this until it ends up with a final reduced result. Now, it turns out that even though this works perfectly well and is thread safe and all the other good properties, it's actually very inefficient, because string concatenation, as shown here, has a lot of overhead because it keeps copying and allocating data to concatenate the strings. So it turns out that there's actually better ways to do this, and we'll talk about the better ways to do it later. But for right now, just be aware that you could do this to return a non-primitive value. So that's the end of the reduce operation. In general, and in my experience, collect is a lot more common than reduce. If you're doing a lot of numeric processing, then reduce is going to be more common than collect. But if you're doing a lot of processing of collections, then surprise, surprise, collect is by far the most common way to go.